Hello, y'all. Welcome to lesson 130 on my DP chemistry curriculum. Today we're going over reactivity 3.4.11 and 12. In 3.411, we're going to discuss how alkenes readily undergo electrophilic addition reactions. We'll describe and explain the mechanisms of reactions between symmetrical alkenes and halogens, water, and hydrogen halides. We learned a little bit about this in halogenation, uh, halogenation, and hydrogenation. Now, with that, we're also going to discuss, or sorry, hydration. We're also going to discuss in 3.4.12 the relative stability of carbocations and the addition reactions between hydrogen halides and unsymmetrical alkenes. And we'll use the stability of carbocations to explain the reaction mechanism. So with that, we'll predict and explain the major product of a reaction between an unsymmetrical alkene and a hydrogen halide or water. We're not going to discuss halogens as we will do that in the first section. So with all that said, let's just go to what we already know, which are alkenes undergo addition reactions. We know they break the pi bond of their double bond to go from an unsaturated state to a saturated state. Um, but the thing is that symmetrical alkenes, which have two identical substituent groups on either side of the carbon-carbon double bond, and unsymmetrical, which have two different substituent groups on either side of carbon-carbon double bond, will produce different products where we can always predict the products of both. The symmetrical and unsymmetrical aspects cause us to look at these reactions differently. So let's start with the simpler one, which are symmetrical alkenes. And in symmetrical alkenes, we're going to start with our halide reactions. Now, the easy thing about halide reactions is it's actually the same for symmetrical and unsymmetrical alkenes. That's because on either side of the double bond, you're still adding the same reactant. So if it's like chlorine, you're still adding a chlorine to each side of the double bond, and it doesn't change anything. So let's take a look at what that reaction mechanism actually looks like. How do we actually explain what's going on? I hinted this in the video about addition reactions before, but now we know a little bit more about the formation of carbocations, and we can explain this a little more clearly. So let's just look at a simple thing like butene, and we will add it to chlorine. Now, chlorine is going to approach butene, or butene is going to approach chlorine, and we have this big electron-rich area. That's going to induce a dipole in the chlorine. As one side gets closer, the electrons will be repelled away, making it positive. This leaves it open to attack. And so the electron-rich area will cause that heterolytic fission to occur. When that heterolytic fission occurs, we get an intermediate. This intermediate is going to have the chlorine that it just created a bond with, but we also form a carbocation. Oops. And so here we have our carbocation, which will be somewhat close to that chloride ion we just formed. That chloride ion is then available for a nucleophilic attack on that carbocation, eventually producing our final product. Oops. C bonded to CH3, HCl, CH3, HCl. And so we can see that this happens in multiple steps. We have a intermediate with a carbocation that is relatively stable. It's only a secondary carbocation here because we only have two carbons bonded around that. So it's not as stable as our tertiary, but it is far more stable than our primary. So just as a recap of what happened here, the alkene induces a dipole in chlorine. Chlorine splits heterolytically, and pi bond in alkene breaks, forming new bond with positive chlorine. Then this ends with the chloride ion attracting to carbocation, forming a coordination bond. So that's our simple addition reaction between an alkene, whether symmetrical or asymmetrical, and a halide. So we can just see it ends up with the chlorine on either side, just like we already learned back in the SL version of this video. Now, as we move to hydrogen halides, this will be different than our unsymmetrical ones. So we're staying with symmetrical here. Hydrogen halides. Now, the reaction mechanism is actually going to be exactly the same, and it will be the same for water as well. Now that we understand what's happening, if we take a look at our butene, we can now predict that as we bring our hydrogen halide close, this already has a dipole with the hydrogen being positive, the chlorine being negative. Nothing needs to be induced. We still get the same heterolytic fission. We still make our carbocation. And I keep missing these threes. And we still then have that electrostatic attraction or that nucleophilic attack of a chloride ion on the carbocation, thus producing our final product, uh, 2-chlorobutane. So with hydrogen halides, it's the exact same reaction we've come to expect back from that SL video, but now we have our detailed reaction mechanism with our carbocation formation. All right, moving on to the water reaction. See if you can predict this one yourself, starting with the same reactants. We're still going to start with butene. The only difference is instead of our hydrogen halide, we are going to bring in water. Whoops, not there. H, bond to O, H. And I've separated out one of the hydrogen bonds just to make this simple. Go ahead, pause the video, try and draw out this reaction mechanism, and then come back, and I'm going to do it right now. So we already have our partial positive and partial negative. So we can see how our bond is going to heterolytically break once again. We are still going to end up with our carbocation. That carbocation is positively charged and will attract the hydroxide we've created, which will nucleophilically attack the carbocation or the electrophile in this. And we end up with our butan 2-ol as our final product. So hopefully you ended up with that. So that's all there is for symmetrical addition reactions. If you got that, which is pretty much the same thing for all three types of reactants, then we can move on to unsymmetrical reactions or unsymmetrical alkenes. Now, with unsymmetrical alkenes, we always have two possible products. And we'll see why in just a moment. But we'll have two possible products, and this depends on which side of the carbon-carbon double bond, which then becomes a carbon-carbon single bond, becomes the cation, becomes the carbocation. And so with that carbocation, we've talked about this before, what really happens is the stability determines favored outcome. Now, I say favored outcome because it's not the only outcome. We're going to still have both possible outcomes and both possible products. One of them will just appear a lot more than the other in solution. So let's look at an example here. If I start with let's say, prop-1-ene, or sorry, just propene, we don't really have to dictate where that is. We can look at CH3 bonded to C, double bonded to C, H, H, and I'm going to kind of ignore bond angles right now. And we have two possible products when we bond with HCl. For number one, and I'll put a number 2 down here to prep myself. For number one, we can have the hydrogen from the hydrochloric acid to move to the secondary spot, or we can have it move to the primary spot. So we'll do the secondary spot first. So what I mean is we have CH3 bonded to C, bonded to H, and then we put the hydrogen here bonded to carbon, and then the chlorine goes here. The other possibility is instead we put the chlorine on the middle carbon, the hydrogen on the end carbon. Now I said secondary and primary because what I'm referring to is this carbon is secondary. It has two carbons around it. Well, this carbon is primary. It only has one carbon around it because we're going to be looking at, once again, the stability of the carbocation. So what this means is we actually have to look at the intermediates formed. Now we know carbocations can be relatively stable sometimes, as we looked at in SN1 reactions. So in the reaction 1, we get a carbocation on the end. So our carbocation's place is at that primary position, if we're using the same language I used before, where we have our HH and our carbocation there. But in 2, we have a different intermediate. It's in the middle position or the secondary spot. Whoops. And the question is, which is more stable? Because the one that's more stable is more likely to occur, and therefore we're more likely to have that as a product. Now, when we're looking at carbocations, we're looking at how well that charge can be distributed to help with that stability. And turns out the secondary carbon can share with both carbons, while the primary can only share with one. Therefore, what's going to end up happening is that if let's switch colors, this is our more stable product. Ooh, the green on blue sucks. Um, we'll just go like this. 2 is more stable. The extra carbon, extra alkyls can share the charge to stabilize it. Therefore, 2 is favored. What that means is that in this reaction, both products will be formed in unequal amounts. That leads to what we call a major and minor products. So in this case up here, we can tell that this is going to be our major product and this is going to be our minor product, and that's due to the stability of that carbocation. So the last thing about this is that we actually have a way where we can often predict this without having to draw out the intermediates, and that is that we can predict with what we call Markovnikov's rule. Markovnikov's rule. Now, the rule basically states that the hydrogen will move to the carbon with more hydrogen. Now, this goes with water and our hydrogen halides. If we look at our previous example, this carbon only has one hydrogen. This carbon has two hydrogens. Thus, the hydrogen will move to that carbon that already has more. So hydrogens want to stick together, or the rich get richer with hydrogen, however you want to look at it. But Markovnikov's rule will tell us how to predict our major and minor products by just put the hydrogen with more hydrogen. Anyways, I hope this helps and have a great day.